Okay, good evening. We are beginning another lecture on sequential modeling using deep networks. We have already finished an overview of what are sequences of information that might be coming in, such as language, and we've gone over the main types of modelings that exist. So now we will take a deeper look at what are called as recurrent neural networks and as to uh, issues regarding how they're structured, how they're trained, and what are some variations on recurrent neural networks and so on. So there are a whole range of topics here. It's quite rich in the number of topics. So today there's quite a bit I'm hoping to cover, given that we won't be meeting next week. So bear with me. I think these are all worthwhile topics because today it seems like the greatest excitement in deep learning is in the area of natural language processing. And natural language processing is powered by the sequential deep learning model. So it's worthwhile to pay attention to all of the methods that have been developed for sequential models. It gets a bit complicated, but I think you can handle it, right? Okay. So I will begin with section 10.1. It might be an overlap from last time. So this is the topic of unfolding computational graphs for RNNs. It's worthwhile to remember what those are. And after that, we go into some nice subtopics on recurrent neural networks, which includes methods for training and so on, right? So let's begin with unfolding computational graphs. Okay, so we saw the idea of a computational graph represented either by a circuit diagram or by an unfolded non-recurrent diagram. Okay, so these are the topics in sequence modeling. We did an overview of recurrent neural networks. We are beginning with unfolding computational graphs. And topic number 2 is also what we'll cover today, recurrent neural networks. But within topic number 2, there are a dozen subtopics. So that's going to keep us quite busy to discuss recurrent neural networks from the basics. All right, so again, reminding what a computational graph is, it's a way to formalize the structure of a set of computations. What are the computations that have to be done in sequence? And we encountered computational graphs when we studied optimization methods, such as backpropagation. And so these computational graphs formalize the structure of computation, such as mapping inputs and parameters to outputs and loss, right? Networks are used to not only compute outputs, but also to compute the loss function so that we can update the parameters. We can unfold a recursive or recurrent computation. So these are two different words, recursive and recurrent. Recurrent is something where we compute something uh, uh, similar to what we had earlier on, and we have a sequence of these computations, common parameters. Recurrent computation is done sequentially. Recursive, of course, the same computation is repeated within a loop. So there is a certain commonality between recursive and recurrent. We'll begin with recurrent. Recursive will come much later. Recursive comes in when we're doing with tree structures. Recurrent is a normal sequential processing, one after the other, where we repeat the computation. Okay, into a computational graph, there is a repetitive structure and corresponding to a chain of events. Unfolding this graph results in sharing of parameters across deep network structure. So we first look at unfolding. All right. So an example of unfolding. So actually in equation like this, state at time t is a function of state at time t minus 1 and a set of parameters theta. It's called a dynamical system, in the sense the state at the present time depends on the state at the previous time, right? And a function maps it from the state at the previous time as well as set of parameters to give us the state now. It's called the state of the system. Equation is said to be recurrent because the definition of S at time t refers back to the same definition at time t minus 1. Right? So for a finite number of time steps tau, the graph can be unfolded by applying the definition tau minus 1 times. So we can write it as a non-recurrent form by simply, let's say tau equal to 3. Supposing we're talking about number of time steps is 3. Then the state at time 3 in the recurrent formulation, it says it depends on state at time 2. But then we plug in the state at time 1 back into this S2 is f of S1. Now it's there's no longer a recurrence here, in that we have a ground state S1. Hopefully we know the value of that. So in a sense, you have to compute this function and so on. So this one calls for another computation, whereas this one would be explicit. S1 is said to be the ground state, and S2 is computed by applying F to that, right? So anyway, this is the process of unfolding is this. And unfolding by repeatedly applying the definition has yielded an expression without recurrence. Such an expression can be represented by a traditional acyclic computational graph shown over here. The classical dynamic system described by st equal to f of st minus 1 theta, and in particular S3 is equal to f of S1 in this unfolded version, is shown as a diagram here as st minus 1 this is S here, st minus 1, function f is operated on st minus 1 to give us st, and then from that we get st plus 1. Note that this f is being repeated again and again, the same function f. Each node represents the state at some time t. Function f maps state at time t to the state at time t plus 1. Okay. The same parameters, the same values of theta are used to parameterize f, are used for all time steps. So this is saying the parameters used by this f not only depends on the previous state, but also a set of parameters. And next time around, we use the same set of parameters here. So we can also generalize this idea of a dynamical system, a dynamical system driven by an external signal, x of t. So now we're writing s of t is f of st minus 1, xt, and x. So we say state now contains information about the whole past input sequence. So the state contains all the information of the past sequence. And we have an input coming in at time t. So this is useful because keep in mind, when we're processing things like strings like language, we are processing one word here. Xt is the tth word, the word that we are given as input. But we have a whole host of memory of what was seen earlier on, and that is encapsulated in this st minus 1. The state is some fixed size vector maybe. So that is capturing all the previous contextual information. And this is a big deal in natural language processing, that we got to remember the past so that we can perform tasks like prediction and so on. All right, so that is a very general dynamical system that depends on state, parameters, and input. So recurrent neural networks can be built in many ways. Much as almost any function is a feed-forward network. If we give any function, we can say, well, I can write it as a feed-forward network. Any function involving recurrence can be considered to be a recurrent neural network. So there are many ways to do this. So we'll slowly build up a little bit of a complexity, defining values of hidden units in recurrent neural networks. So many recurrent neural networks use same equation as dynamical system. Dynamical system is a very general formulation. So deep learning is a new subject, right? It didn't exist, maybe 10 years ago, right? So we are now replacing S by H. H stands for hidden. So this equation is the same as before. We just replace the S, the state, by H for hidden. So we can think of it as a neural network where we have some hidden units here and input X theta, that we all know. And we have here a diagram. This is a circuit diagram. We are saying X goes to H. There is some kind of remembrance going on from the previous input that you gave me. These are all X's taking on new inputs. And the same function F is operating on each of them and changing the state. And it is using the previous state and updating it. The same set of parameters are operating on it. So this is what happens in these recurrent neural networks. When we unfold it, it becomes some state here, and then this is ht minus 1. So ht minus 1, we have xt minus 1 coming as input. This ht minus 1 is provided as input, and f operates on ht minus 1 as well as xt is the current. So this is the equation here that's going on. ht minus 1 and xt, and the same set of parameters, theta, produces ht plus 1, and so on. Typical RNNs have extra architectural features such as outputs. This one is not showing any outputs. As output layers that read information out of state H to make predictions. So we could say, well, you are giving me words of English, right? And maybe the hidden states are somehow being produced from these, and from these hidden states, maybe we can be producing outputs at every point, right? We saw some German words and converted into English words. So English word coming out, English word coming out, English word coming out. And these are German words over here. Of course, the variable length becomes an issue. So the same thing, I guess it's repeated what we just saw. This network just processes information from input X by incorporating into state H that is passed forward, right? So state H is passed. This is referred to as a circuit diagram. Black square indicates delay of one time step. And unfolded computational graph is this one. So this kind of explicitly tells you what are the computations you need to be able to predict the next edge or predicts the next output, so on. Typical RNNs will add extra architectural features such as output layers to read information out of state edge to make predictions. When RNN is required to perform a task of predicting the future from the past, network typically learns to use HT as a lossy summary of the task relevant aspect of the past sequence of inputs up to T. So the next output it's going to produce is based on some kind of a representation we have. H is a representation. The summary, that's a summary of what was seen before, is in general lossy since it maps the sequence of arbitrary length to a fixed length vector HT. So a fixed length vector is holding all the knowledge of what was seen earlier on. And so it's going to be lossy. It's not going to have explicitly, and it could be variable length coming in. All of that is getting compressed into a fixed length vector HT. So that is the summary, the information contained in the summary. Depending on criterion, summary keeps some aspects of the past sequence more precisely than other aspects. So we're going to be subjecting it to all kinds of procedure for learning, and so we'll be using a certain length of the hidden unit, right? How many hidden units in the hidden layer, and it's going to be compressing into those values. And in what way it's going to be compressing them, it depends on the kind of loss function we're going to use to train it. RNN used in statistical language modeling typically to predict next word from past words. So we may want to predict the next word from past words. It may not be necessary to store all information up to time t, but only enough information to predict rest of sentences. We might call upon it to predict the next word. So we are guessing what the next word is. And that can be useful, I suppose, in some kind of a recognition circumstance where we are narrowing down the possibilities. Let's say we're trying to recognize handwriting. And here is something coming up. What's coming up next? Okay, all the previous words predict what's going to be the next word. We also have an input coming in. So we can say, but the possibilities is much reduced because of the context. And so we get a more precise output. So in that sense, that is also a method of prediction. Most demanding situation is we ask HT to be rich enough to allow one to approximately recover the input sequence as in autoencoders. So we may actually end up asking it to recover, and autoencoders have to recover what was input. So that is an extreme situation. So anyway, we have another diagram on unfolding here. Let's see, we see all this. Unfolded graph has a size dependent on the sequence length. Okay. All right. So the unfolding process introduces two major advantages. Regardless of sequence length, learn model has the same input size. And we are using a certain length output here. And we're using the same function f, the same parameter at every step. So it is these two factors make it possible to learn a single model f that operates on all time steps and all sequence of lengths rather than needing a separate model GT for all possible time steps. So we are kind of deciding to use a certain sequence of in the past and use that to predict the future. Learning a single shade model allows generalization to sequence lengths that did not appear in the training. If we had got a function that was not recurrent, we would have to keep on coming up with new functions for different sequences. So the compaction is being achieved here by a common function, by a common set of parameters, and we are actually predicting something based on a certain length of sequence that's coming in the past, that came in the past. So both recurrent graph and unrolled graph are useful. Recurrent graph is succinct. Unrolled graph provides explicit description of what computations are performed. Yeah, why don't we just use the circuit diagram? Fine, it tells you what is going on, but explicitly what are the relationships and so on that exist are better obtained by looking at the computational graph. Helps illustrate the idea of information flow forward in time, computing outputs and losses, and backwards in time, computing gradients by explicitly showing path along which information flows. We saw when we were doing backprop that some of the implementations call for explicitly storing the computational graph. And so once you know the computational graph for the problem, it's not just an abstract concept. We can explicitly have it stored. And when you have to do backprop, you can use that so that you know what computations to perform next. Okay, so now we are into a computational graph for a full network here. We've seen something like this before, but let's go through it again. X goes to a hidden unit, input X in the hidden unit X, and there is a matrix W that operates on H from the previous time step goes on to become another input here. And what is this H? It is a tan H of A, all right? So there is some A coming in. And what is that A that's coming in? Is B plus WHT minus 1. So it's taking into account the state. And UXT, that is what is the input. And so it is a linear function. A is a linear function of WH and UX. And then we make it nonlinear by applying a tan H function to that A, and that is the value of HT, is that value. It is this nonlinearity that's so powerful in computing any function we want. So x goes through h, and then the value of h after desired number of time steps, we use it to all generate the outputs, right? So O is again a linear function of h, right? C plus VH. You see, this is a very common phenomenon with deep learning networks, that we have nonlinearities at all levels. And the final level to generate the output is possibly just a linear function, right? A linear classifier, like logistic regression type of thing, to have two-class output, or a sigmoid, or a softmax version to have a multi-class output. So that is what's going on here, output. And we show L like this and say, okay, L is a loss computed by Y, which is the desired output. O is what is the model output. And unfolding, we are showing it like this. So we're going from HT minus 1 to HT to HT plus 1. So you see, we have outputs coming out. So it could be, for example, these are English words, sequence of words, the birds fly, right? So the birds fly. And they are being mapped into the equivalent words in German, would be those three words here, right? And we are mapping what the model is outputting, and say, well, that should have been a certain German word. And we are comparing the two and say, hey, there's a loss here. All right, so there's a loss here, and then there is going to be a loss here, there's going to be a loss here. So somehow all these losses have to be, we have to compute derivatives and need to back propagate them to update all the weights, W and V. So there's a lot of computation that needs to be done. We can unfold a recursive or recurrent computation into a computational graph that has repetitive structure corresponding to a chain of events. Unfolding this graph results in a sharing of parameters across a deep network structure. Oh, I found this nice diagram. It was just a company that was advertising itself. Indico Corporation is on their website. I don't know if that company exists anymore. I think I made this slide a few years ago. This showed a recurrent neural network. The time t minus 1, time t plus 1. And here are a couple of input. They show explicitly, not just by one node, by two nodes here, as if it's a neural network with 3 units in the hidden units, 2 output units. And you see all these units here are transforming these 3, the next state, right? HT minus 1 becomes is used to update to get HT. And we are also using the inputs here. But more generally, the diagram we saw was not exactly the same thing. But this is the computational graph we saw, that is xt minus 1 to ht minus 1. So you can think of the xt minus 1 as these 2 units here. ht minus 1 is these 3 units here. OT minus 1 are these 2 units here. But then what happens at the next stage, the way they've shown, I'm not sure it exactly captures this idea, where we are taking this vector here and multiplying it by a matrix. So all of these values influence to get this. Maybe they've shown that as this influence here. Maybe that's okay. And similarly, a matrix multiplication is what is used to generate O, so on, right? So this is the computational graph version. Okay, so that's the basics of unfolding computational graphs. And we shall close that one. Okay, and we will go on to the next unit, which is 10.2.0. Oh, I went off to some wrong one here. It was 10.2.4. I needed 10.2.0. Okay. Okay, I hope you can see this one properly. It's recurrent neural networks. If not, you can speak up. Okay, so we finished unfolding computational graphs. And we're beginning this recurrent neural network, which is a number of subtopics in it, 10.2.0 to 10.2.10 or something, quite a few topics there. All right, so what are the topics in recurrent neural networks we want to study? Here again, an overview, design patterns for RNNs. We just saw something which looked like a standard design patterns for RNN, but there are some variants here. Should we connect the hidden units from one stage to the next stage, or should we connect the output units from one stage to the hidden units? That sounds like a strange thing, but it seems like it's it simplifies lots of things if we do that. And here, so those are design patterns. And then RNN with recurrence between hidden units. Forward propagation equations. Yeah, if you want to learn about training these things, we need forward propagation, and then we need something about loss function for a sequence, and RNN with the recurrence from output units to hidden unit. That's the one I talked about, from output units to hidden units. So it's a different kind of design. It's a different design pattern than what we just saw. And training for that is interesting. And what happens when you're using outputs at one stage as input to the next hidden unit, while it makes things computationally simple, it ends up leading to a lot of problems in terms of training. So if one level you're outputting something wrong, it has got implications down the line. So to avoid that, there's a method called teacher forcing. Remember, we're talking about learning or machine learning. So we even have a machine teacher here, right? I guess a human teacher. This is a supervised learning. So we have teacher forcing. That is, we instead of just using the previous hidden state or the output value, you are going to use the correct value. So it's called teacher forcing. And computing all the backprop with all of that, it's a specialized version of backpropagation. So this is backpropagation through time called BPTT. As you can imagine, we're going to need that. Standard backprop is not going to work here because we're going to go through several stages. And then there are all these other topics, computing the gradient in an RNN. RNN as a directed graphical model. So RNN itself can be thought of as a graphical model, which those if you're familiar with that topic, it's about representing probability distributions for symbolic computing. And then modeling sequences conditioned on context with RNNs. So context is the big issue. These latest attention models and so on. Before we get into the practicalities and talk about NLP, we also want to speak of context, and that idea is used there. All right, so again, graph unrolling, parameter sharing in RNN design. We talked about this already, that HT at any point can be expanded, can be written as GT of XT, XT minus 1. Yeah, this is the completely unrolled value of H. And we, instead of doing it GT of all of the inputs, we are summarizing what was seen in the past by HT minus 1 and then take XT as the input at theta. Function GT takes the whole past sequence as input and produces the current state. But the recurrent structure allows us to factorize GT into a repeated application of a function f. That's the cleverness here. So it is not that we are learning a function which, let's say we were trying to do English to German translation. If we use this idea of GT, we'd be training it by, okay, for this sequence, this is the output. For this sequence, that is variable lengths. And so we'd have to have, there is no nice structure to it. Whereas this formulation saying, okay, we're just looking at it stage by stage by stage with a fixed set of parameters at each stage, looks like this is a much more elegant solution than the cumbersome way of dealing with the entire sequence as input to produce the output. All right, it does not need a separate model GT for all time steps. The function becomes different for a shorter sequence, and so on. Whereas here, we'd have some commonality. Process of unrolling and parameter sharing allows us to design a wide variety of RNNs. Examples of important design patterns. So there are multiple design patterns which are shown here. 3 design patterns of RNNs. So this first one is what we just saw. There's number one here, number 2 here, and number 3 here. Number 1 produces an output at each time step and has recurrent connections between hidden units. So this is the recurrent connection between hidden units, and we are producing an output at every input. The second model says produce output at each time step and have recurrent connections only from output at one time step to hidden units at next time step. So there's no connection between the hidden units here. Hidden unit is a big vector here. Producing an output, well, can't we use what was output before and use that as input, all right? So this is just using what was produced, and that brings in some kind of simplification when the full process of dealing with the full memory of the hidden units. Recurrent connections between hidden units to read the entire input sequence and produce a single output. Okay, this is a different type of task where we are continuing with all the hidden units influencing each other. And we go over to this last part, and the very last output produces very last hidden state produces an output, and we have a loss function comparing what should have been output and what has been output. What has been output by the model? There's a loss function. You can imagine that this could be something like sentiment analysis, right? There's an input coming in, sequence coming in, and we're reading it, and we are absorbing what is being said from one word to the next word to the next word, and finally we output, that's a positive sentiment or a negative sentiment. So some kind of a single value, as opposed to some of these are all producing machine translations, which is a sequence to sequence problem. This would be a sequence to symbol. So this slide we already saw. It is simply saying design one RNN with recurrence between hidden units. We just saw that. This is the circuit diagram. This is the unfolded recurrent diagram. And we saw how we go from HT minus 1 to HT to HT plus 1. And okay, in this slide, we'll just take a look at look at the loss and all the equations. Maps input sequence X to output sequence O here. Loss L measures how far each O is from corresponding target Y. This is the target Y, this is the output. That's what loss is measuring. With softmax outputs, we assume O is the unnormalized log probabilities, right? So it is computing some set of values here. It's a softmax. Softmax is operating here, which is computing probabilities and some values, unnormalized log probabilities, and those are going to be normalized by softmax. Loss L internally computes Y equal to softmax of O and compare. So it is computing the softmax of all of this and compares it to these Ys. That's how this value is decided. And the update equations are, once again, O is C plus VH. This is a linear model. O is just a linear function of the H. And then H is a nonlinear function of A. What is A? A is simply a linear function of the H, previous H value, and the X value. And what is y hat of t? So in this case, at time t, we are going to be computing y hat of t, which is the output here from this O, y hat of t is a softmax of all of these O's to give y hat of t. Li compares, LT compares y of t and y hat of t to say how different they are. An observation here is that an RNN with hidden unit recurrence is a universal Turing machine. Oh, wow. This is getting into theory of comp here. This is saying a model like this, where we have these H's interacting like this, an RNN with hidden unit connections together with what we just saw, the activation, and is universal. That is, any function computable by a Turing machine is computable by such an RNN of finite size. How does this fit in with the other theorem we saw? We saw the a theorem that one hidden layer is sufficient, and we called it as no, anyone remember the exact title of that? Universal
approximation theorem.
Huh?
The universal approximation theorem.
Universal approximation theorem. Okay, that was escaping me. All right, the universal. Yeah, thanks for speaking up. Speak up, if you feel like you want to ask a question also. Thanks for helping me out there. Universal approximation theorem, and this is very similar to that. So there's not a surprise that this is because we say any function can be computed by universal approximation theorem. Any number of so you can have. Yeah, that one was talking about one hidden layer. So if you have more hidden layers, great. And this is saying if you have one more variable coming in, the function is a function of time also. Then this is saying this is the exact equivalent of that. So generalization of that. So it's good to know that this can compute any function you want of mapping input to output of the kind described here, input sequence to output sequence. So anyway, universal, yeah. So any function computable by a Turing machine is computable by such an RNN of finite size. That's interesting also, a finite size. You don't have to have a infinite number of steps for the T's, right? The tau can be a finite. So output can be read from the RNN after a number of steps asymptotically linear in number of steps used by the Turing machine, and asymptotically linear in length of input. So there is a more explicit connection about this. It'd be interesting to look at the theorem that proves this. Okay, anyway, those of you who are inclined theoretically, maybe Kedar Raghavendra Rao can look at this, right? All right, now let's see. Forward prop for RNN with hidden unit recurrence. This design does not specify activation functions for hidden units, form of output, loss function. All right, so you can throw in whatever you want on these things: activation function, form of output, and loss function. Assume for this graph hyperbolic tangent activation function. We just saw that hyperbolic tangent, that tan H is called hyperbolic tangent activation function. Output is discrete. Example, RNN predicts words or characters. The output could be, individual characters coming out of a box, or it could be words coming out of a box. Natural way to represent discrete variables. Output O gives unnormalized log probabilities y hat of each possible value. Can apply softmax as a post-processing step to obtain vector of unnormalized probabilities. And forward prop begins with specification of initial state H naught. So forward prop is simply processing these inputs. That's forward propagation, right? That's not back prop. And we begins with specific initial state H naught. So you need to have some specification for that. So the forward prop equations for our RNN with hidden recurrence, we just saw that, O, H, and A, and Y hat, we saw all this, where the parameters are bias vectors B and C are also coming into play. Weight matrices U, input to hidden, V hidden to output, and W hidden to hidden connections. So these are all the forward prop equations with hidden recurrence. What about loss function? Case of RNN that maps an input sequence to an output sequence of the same length. So we are specifically saying same length output sequence. So we are just mapping a sequence of words or sequence of inputs to a sequence of outputs of the same length. Total loss for a given sequence X of values, the sequence of values is the sum of the losses over the time steps. So if LT is a negative log likelihood YT given X1 through XT. So we have loss of X1 through XT, Y1 through YT. So what is the loss encountered here? Well, it's the loss at each time step summed over all the time steps. And what is the loss at each time step? Well, we can think of it as there is a model that we are dealing with, and the model is assigning a probability to YT given X1 through XT. So we are taking this as and then the logarithm of this probability is being taken. It's a negative logarithm. So it becomes from a problem of loss minimization. And I guess this becomes a maximization problem if you make it a negative here. And we are using log probability. So this kind of arises from a probabilistic formulation of the problem. And the loss is just, and this summation is overall steps T. And we are actually using, actually it comes out of maximum likelihood. That's where it comes out. So to make it a loss function, that's how this negative comes in. So the loss itself is, so this negative came about because this is a likelihood, log likelihood. That's what it is. And when you have log likelihood, we want to maximize that. But we want a loss function you're going to minimize. So that's why we add this negative over here. So this is how we could set it up. And of course, we might be using some Bernoulli type of function here and all to as the basic model that comes into play. So anyway, we have a way of setting up the loss function, and then we also need to have a way of computing the gradient. The only reason to set up a loss function is we need to learn the weights and we need to compute the gradients. Computing gradient of this loss function with respect to parameters is expensive. As you can imagine, there is so much more other than the usual network. We also deal with the time thing. It involves performing a forward propagation pass moving left to right through the unrolled graph, followed by a backward propagation moving right to left through the graph. So we got to have forward prop and backward prop. Runtime is order tau, that is how many steps we're going to look at, and cannot be reduced by parallelization because forward prop is inherently sequential. Each time step computable only after previous time step. And states computed during forward pass must be stored until reused in backward pass. So you're going to have to remember the values of the states. So memory cost is also order tau. So this is runtime is order tau, memory cost is order tau. Back propagation applied to the unrolled graph with order tau cost is called backward propagation through time. So this is a specialized topic in backprop called BPTT, where you're dealing with backprop involving these types of gradients. All right. So this is a topic by itself, so we're not going to say much at this point. RNN with hidden unit recurrence is very powerful, but also expensive to train. Is there an alternative? Okay, we say, stay tuned, folks. Is there an alternative? All right. Okay, let's go on to 10.2.1. I think we just finished 10.2.0. We're going to go to 10.2.1. Oh, this is a very interesting topic, 10.2.1. Okay, this is teacher forcing, right? So this is saying the backward propagation through time is expensive. So we're saying maybe there's a solution to this. So we are looking at, we just finished an overview, and then now we are looking at teacher forcing in networks with output recurrences. So models with recurrence from output to hidden. It is less powerful than hidden to hidden recurrent connections. Right? Because when we produce the output, we kind of compressed even more, and we lost some information, and we are getting just for this input what's out. It's not remembering a whole lot of things from the previous stages and so on. So this is less powerful. It cannot simulate a universal Turing machine. Oh, okay, all right. So it is not as powerful to compute any function you want. It requires that the output capture all of the information of past to predict the future. If you're saying this word is translated to this coming word, does that capture all the previous words? I guess not. It's just the local information it is produced. An advantage of this kind of a model, see, look at there's no connection between ht minus 1 to ht and ht to ht plus 1. There's a connection from ot minus 1 to ht and ot to h. That's the difference. These are diagonal lines instead of horizontal lines. Advantage in comparing loss function to output, all time steps are decoupled. Each step can be trained in isolation. Right? So this is saying there's a decoupling going on. Each time step can be trained in isolation. Training can be parallelized. Right? We can do all of these in parallel. And gradient for each time step t is computed in isolation. And you can figure out all these weights here. And no need to compute output for the previous step first, because training set provides ideal value of the output. So we know the ideal value of the output. So we don't even have to, you don't need the previous output. No need to compute output for the previous step first. All right. So we can just use each stage separately. And can be trained with the teacher forcing. All right. So this is an important concept. How important is this teacher forcing? RNNs in NLP use teacher forcing in the training process, in image captioning and machine translation. If you go to the TensorFlow tutorial on neural machine translation with attention, okay, it's a very current topic. So if you go look at how do you do neural machine translation with attention, it says teacher forcing is the technique where the target word is passed as the next input to the decoder. So it says if you use their neural machine translation code using attention models, they're using teacher forcing. Okay, so this is motivation to say, hey, better look at what is this. So what is this intuition of teacher forcing? Is maybe you've all been subjected to this when you take the quizzes and when you take the midterm exams or the final exams, and you might have a math exam question with multiple parts, A, B, C. Answer for part A is needed for the calculation in part B. Answer to part B is needed for part C, and so on, right? You know that. So there is a teacher has set a question with these kinds of questions in it. If we get part A wrong, then all the subsequent parts will most likely be wrong as well, even though the formulas and calculations are correct. So if you got the first one wrong, all the rest are wrong. Teacher forcing remedies this as follows. It says after we obtain an answer for part A teacher will compare our answer with the correct one, record the score for part A, and tell us the correct answer so that we can use it for part B. That's a different kind of online exam, I suppose, where only after you answer part A, you will be given the answer to part A so that you can use it for part B. So that is where that's the teacher forcing part. The teacher is saying, don't use your previous answer. I will tell you what the correct answer is, which is the forcing part of it. Image captioning example. Okay, we have a teacher and a student over here in this picture. Ground truth caption is two people reading a book. And supposing we have a model which is predicting these words. So it says instead of it's predicting these words, it predicted for the first word, the output is 2. Maybe we're doing a machine translation and we're supposed to get 2 as output. It got 2, but instead of saying people, it said birds for the first 2 predictions. And without teacher forcing, if we don't use teacher forcing, the birds in the RNN is used to predict the third word, right? So it's saying start, it's predicting 2 here and 2 is being used. RNN produces birds as the second word. We're using birds as this one. And then when it encounters birds as the previous word, RNN may say next word is flying. So instead of becoming 2 people reading, it became 2 birds flying. As opposed to teacher forcing, we start, produces 2, and 2 is now being used here through the RNN. Okay, even though it produces birds, we don't use birds at the next level. We're saying the ground truth is telling us it is actually 2 people. So people, when you say 2 people, what could it be? It could be 2 people running or 2 people, whatever, reading. All those possibilities exist here. So this is the example of teacher forcing, where we're using ground truth to make these predictions. And whereas the network is using, and we're ignoring that previous output, but still that previous output is useful for other operation. So pros and cons of teacher forcing. Training with teacher forcing converges faster. At the early stages of training, the predictions of the model are very bad. If we do not use teacher forcing, the hidden states of the model will be updated by a sequence of wrong predictions. Errors will accumulate. It's difficult for the model to learn from that. Cons are that during inference, since there is usually no ground truth available, the RNN model will need to feed its own previous prediction back to itself for the next prediction. So we may need, in a situation where we don't have ground truth available, to be able to do that. So there is a discrepancy between training and inference. Inference is predicting in the future, and we are using inputs without ground truth. This might lead to poor performance and instability. So this is known as exposure bias in the literature. So there is some issue here about the availability of the ground truth information or not available, and then you would be using the previous output as input. We're using that second model we talked about, where the hidden units are not connected directly, but we're taking the output. So teacher forcing is used to train models with recurrent connections from their outputs. And teacher forcing during training means instead of summing activations from incoming units, each unit sums correct teacher activation as input for the next iteration. So the teacher forcing procedure for training RNNs with hidden recurrence, it again, and how do you set it up with teacher forcing? It emerges from the maximum likelihood criterion again. During training time, model receives ground truth output YT as input at time t+1. We can see this by examining a sequence of 2 time steps. Consider a sequence of 2 time steps. The conditional maximum likelihood criterion is, again, we're using the log likelihood, P of y1, y2. Sequence of 2 given x1, x2 can be written as y2 given. So this is a simple application of the product rule of probability, that joint probability can be written as the right, and then we're taking a log of it, right? So this is the product of these 2 quantities. And when you take a log of it, it becomes log P and log P. So product has become sum here because of the logarithm here. At time t equal to 2, a model is trained to maximize the conditional probability by 2 given both the sequence x1 so far and the previous y values. We're using y1 as teacher forcing rather than only x1. And maximum likelihood specifies that during training, rather than feeding the model's own output back to itself, target values specifies. So this says you are playing around here with the values of y1 as we're using teaching forcing here, okay? So this is again teacher forcing is being shown here diagrammatically at training time and test time. Teacher forcing is a training technique applicable to RNNs that have connections from output to hidden states at next time step. So training time, we feed the correct output YT from teacher drawn from the training set as input to HT minus 1. All right, so this is YT minus 1. As you know, it's the supervised learning. So that is the teacher has provided that. So we are using that during training time, right? And during test time, when you have a new input, true output is not known, right? We are now saying, okay, while training, we know the machine translation problem here. So we know exactly what word you should be getting and we can let you figure it out. And this is saying, well, now you have a new example that please translate it for me. I don't have ground truth. So we approximate the correct output YT with the model's output. So we are taking the model output back here. So there's a difference in the training time. We're using ground truth and here we're using just the output. So there is all kinds of material. I found this on Quora actually. What is the teacher forcing in RNN? Because it's used and people want to know what is this. And there's all kinds of interesting diagrams people have drawn here of, I guess the same things we saw, RNN at time t. All right. RNN at, okay, anyway, this diagram, is it time t equal to 1, 1, 1? No, it should have been 1, 2, 3, maybe. All right. So without teacher forcing, and this is with teacher forcing. So they're giving a little bit more detail here on the same kind of diagrams we just saw, but you know, I saw it another interesting block diagram of that. Visualizing teacher forcing. Imagine that the network is learning to follow a trajectory. Trajectory in the sense we are talking about the weights have to follow along a trajectory, like the dotted lines here. And instead of it goes astray because the weights are wrong, and so we keep, you know, heading along like this. You know, some other place we're ending up. And what teacher forcing is doing is by setting the state of all the units. So it is telling it that this is the correct value, go here, and again it's going over here. This is the correct value, go here, and so on. So it kind of shows in a diagrammatic way what this is. Teacher forcing for hidden to hidden. Oh, okay. We originally motivated teacher forcing as allowing us to avoid back propagation through time in models that lack hidden to hidden connections. Teacher forcing can still be applied to models that have hidden to hidden connections as long as they have connections from the output at one time step to values computed at the next time step. As soon as the hidden units become functions, the earlier time steps, PPTT algorithm is necessary. Okay. So, you know, nowadays people are all just routinely using all these RNNs with attention models and so on. But this is under the hood. What's going on is teacher forcing with BPTT and so on. Training with both teacher forcing and BPTT. Some models may be trained with both teacher forcing and backward propagation through time. When there are both hidden to hidden recurrences as well as output to hidden recurrences. Oh, everything comes with advantages, disadvantages. If network is to be used in an open loop mode with network outputs fed back as inputs, in this case, the kind of inputs that we will see during training time could be quite different from that it will see at test time. Yeah, we trained it at training time with all these language sequences with the ground truth and so on. But when you are in a open loop mode where we just have to use the previous outputs, those could be different. And solutions to mitigate this problem: train with both teacher-forced inputs and free-running inputs. Example, predicting the correct target a number of steps in the future through unfolded recurrent output to input paths. Network can learn to take into account input conditions not seen during training. All right. And so we are saying as we are generating something, we are taking into account what was in the past. And it says you have to now use the values that you are encountering in the free form as opposed to training mode. So mitigate the gap. Hey, welcome, Mohammed.
Hi, Professor. Thank you.
Okay, good. All right. Mitigate the gap between the input seen at training time and test time to generating values as input. So there is something here called curriculum learning strategy. So there's so many analogies with human learning. Okay, this last slide in this section is teacher forcing versus professor forcing. All right. What is this stuff? We talked throughout here about teacher forcing. Teacher forcing trains RNNs by supplying observed sequence values as inputs and using network's own one step ahead predictions to do multi-step sampling. All right. So the outputs are probabilistic. That's where the sampling comes into play. But we just saw what is teacher forcing, where instead of using the output at the previous step, we are using the ground truth value. What is this? This professor forcing was described in a paper by some of the authors of the deep learning textbook, Bengio and so on. It is an interesting paper. They say they bring in the idea of adversarial method, the idea of GANs here. So this says uses adversarial domain adaptation to encourage the dynamics of the RNN to be the same when training the network and when sampling from the network over multiple time steps. So we are going to be using what the model has generated. So there are two types of inputs coming in, right? We have the prediction from the model, and then from the ground truth, we have a prediction too. So in a way, it makes a scenario similar to data coming from the training set and data coming from the model, right? So the job of the discriminator is say whether it came from the model or from the training set. And we have a similar type of thing going on here, that the model says something about the previous output and the previous output is influencing the decision at this step. But there is also the ground truth telling you exactly what it is. So we have two types of inputs, and somehow the adversarial nature of these can be taken into account and come up with a new method of teacher forcing. And they wrote a paper a few years ago on this. I don't know how widely used it is, but so it says idea of adversarial training has come into teacher forcing here, right? So you may want to look at that. I don't think these topics are discussed that widely today by practitioners. They'll say, okay, somebody takes care of the training part for us, right? The backdrop is all done under the hood. But if you're going to be using an RNN, or you're using any kind of RNN with LSTM or RNN using attention models, backdrop is an essential thing, right? So you have to have a method to deal with it. And so this is something that is absolutely essential, but may not be something that every user becomes aware of. I guess users don't need to be aware of even backprop also, and simply use it. Okay, so we'll continue our miscellaneous topics in RNNs. We just finished 10.2.1. So we'll go to 10.2.2, I suppose. Computing the gradient in RNN. Okay, so some of these are interesting things to be aware of. Not that you're going to become a specialist in computing the gradient in RNN. It looks like a pretty complicated topic. So this is, yeah, we just saw teacher forcing. And now we are looking at computing the gradient in an RNN. All right. Training an RNN is straightforward. And determine gradient using backprop. Apply generalized backprop to the unrolled computational graph. Algorithm repeated, next slide. No specialized algorithms necessary. Gradient descent is gradients obtained by backpropagation are used with any general purpose gradient based technique to train an RNN called BPTT, backpropagation through time. So general backpropagation to compute gradients T of a variable Z with respect to variables in a computational graph. We saw what the computational graph looked like. Require T, the target set of variables whose gradients must be computed. Require G, the computational graph. So we need the computational graph we talked about for the RNN. And let G prime be G prune to contain the only nodes that are ancestors of Z. Okay, Z is the variable to be differentiated. All right. So this is the outermost skeleton of the backprop algorithm. This portion does simple setup and cleanup work. Most important happens. Build. Oh, okay. This is, I took this way out of the earlier chapter. This is not specific to RNN. This is the basic general backprop. Okay, we know this stuff already. Build grad function and so on. It gives all the details of that. I think I borrowed these slides from an older part. Now I'm beginning to look at example of how BPTT algorithm behaves. Backpropagation through time. We saw these equations. We saw the equations used in an RNN, and we saw the loss function in an RNN. We provide an example of how to compute gradients by BPTT for the RNN equations. Intuition of how BPTT algorithm behaves. Gradients by BPTT for RNN equations given above. Nodes are, we just saw this UV, and then the parameters UV, W, B, C, as well as sequence of nodes indexed by T. For each node N, we need to compute the gradient derivative of L with respect to N, right? For every node, we need to know what is the derivative with respect to the loss function. We saw the definition of the loss function. Computing gradients, BPTT gradients recursively, start recursion with nodes immediately preceding final loss. All right, we start with the final loss over here, LT plus 1. We assume that the outputs OT are used as arguments to softmax to obtain a vector Y hat of probabilities. And then what are we saying here? Also, that loss is the negative log likelihood of the true target given the input so far. The gradient on the outputs at time steps T is given by here, this quantity with the output, okay, OT of L is L with respect to OI, right? That partial derivative. And that can be written as this by chain rule. And that's the first step. Work backward starting at the end of the sequence. At the final time steps T, HT has only OT as descendant. And so derivative of H with respect to, of L with respect to H is V. This is, we are multiplying this matrix. This has the same flavor as a product of the gradient times the, what was that? Laplacian times gradient, that kind of thing is going on here. Gradients over hidden units, what they look like. All right, so we have these derivatives. Now we're talking about derivative HT plus 1 with respect to HT. That's interesting. We hadn't seen that before. and output with respect to HT and so on. So these are all the equations, and where diag indicates diagonal matrix is the Jacobian of the hyperbolic tangent. Like Jacobian, if you remember, it's all the matrix of partial derivatives. And so this is the Jacobian matrix of partial derivatives available with respect to T's. Gradients over parameters, C, B, V, W, U, these are all the equations. They're not all that complicated. Ah, that's it. Okay, so moral of that story is these are all the specialized equations for learning a sequential model, right? I mean, you can't get away from this stuff. With even attention models and so on, you would have to be using these things. Okay, we're going to go on to appreciating RNNs, and we will go to 10.2.3 next. And oh, this seems to be not such a necessary topic. Let's see how we're doing on time. RNNs as directed graphical models. Oh, let me just touch upon it for those who are interested in these kinds of things. So the topic is RNNs as directed graphical models. So we can think of, now those of you are familiar with graphical models, that's PGMs, right? 674 is what we cover that. And which is, they're all methods for representing probability distributions by graphs. And they're different from neural networks in that directed graphical models, the nodes correspond to variables and the edges in a directed, if it's directed, right? Directed means there is a parent-child relationship between two nodes. And a directed model means there's a conditioning going on, that the parent, the child is dependent on the parent. So we can write a joint probability distribution by multiplying all the conditional probabilities in the graph. And that gives the joint probability of all the variables. So it's kind of intriguing to say RNNs as directed graphical models. If each of the nodes corresponds to a variable, can we talk about a probability for any given set of assignments to every value in the network? So that is the intriguing part here. So we are on to here 10.2.3 RNNs and directed graphical models. Okay, motivation for this topic. Why do we care about it? What are directed graphical models? Okay, that's a small tutorial on a topic of a whole course. RNNs as directed graphical models. So what are the conditional probability? Conditioning predictions on past values and fully connected graphical model for a sequence. Hidden units as random variables. And efficiency of RNN parameterization. How to draw samples from the model. Now that becomes interesting because sampling is an important topic in deep learning and generative models do that. So this being motivated here as from a task of images to text. So for instance, here is an image and that is being translated into the caption that says a group of people shopping at an outdoor market. There are many vegetables at fruit stand. So there is a caption generated by a recurrent neural network. And what does it take as input? Representation generated by a deep convolutional neural network. It's a computer vision part, which is a deep CNN is producing a representation. It's a representation, right? So it is some representation obtained. RNN trained to translate high-level representation of image captions. So it is high-level images into captions. So an RNN has been trained to take this as input, representation as input, and to produce words as output. And the axis, I suppose, would be the representation here in our RNN, and the Y's would be the output text here. And it's a language generating RNN here. So they show that this is a recurrence here going on, that it is scanning through the words that are being generated at each step depend on the previous words and so on, right? I saw some examples of this whole area. Better translation of images to caption, different focus, lighter patches given more attention, right? So it kind of brings in the attention model in a visual domain. A woman is throwing a frisbee in a park and there is a higher attention to this part of the image. A dog is standing on a hardwood floor and the dog part is, I suppose, here. A stop sign on a road with a mountain in the background. The stop sign is being paid attention here. A little girl sitting on a bed with a teddy bear. So the little girl is the focus here. A group of people sitting on a boat in the water is this part. A giraffe standing in a forest with trees in the background. I guess this is the black part here is attention maybe. As it generates each word in bold, oh, there are words in bold. So frisbee is what's being highlighted, dog, and then stop is being highlighted, girl is being highlighted, people is being highlighted, and oh, this is not focusing on the giraffe, it's focusing on the trees. The light part is the trees in the background. As it generates each word bold, it exploits it to achieve better translation of images to caption. I think this is probably more on the attention model issues, but it's again the problem of going from combining CNNs with RNNs, CNNs for vision with RNNs for language. So that was the motivation given for this. There is some issues about the dependencies between words, I suppose. And this is a bit of a tutorial on a directed graphical model, like a joint probability distribution is written as a product of conditional probabilities. Xi given parent of Xi, that's what this notation means. These are conditional distributions. So you're running through all the n variables. And if they're all independent variables, there is no conditioning. So it just becomes the product of all the variables in the for this joint distribution. But if there are conditional probabilities, we take that into account. And once we have a network, this can be written as a graphical model where nodes correspond to the variables, conditional probabilities correspond to links with parent-child relationship. It becomes a graph. And from such a graph, it is straightforward to generate samples using ancestral sampling. You run through all the variables from 1 through n. Each time generate values for each variable. And if there's conditioning, you have to generate from the conditional probability. We will see here that RNN have an interpretation as an efficient directed graphical model. RNN is an efficient directed graphical model. This is a classic example I use in the 674 course. I think I borrowed this slide from that course of what a graphical model is. It's got 5 variables here, and there are these variables with their own marginal distributions, and these are conditional distributions given the parent and the child. What is the conditional distribution of grade given difficulty and intelligence? And then similarly, there is, these little tables are the conditional probabilities, and together they represent the joint probability of all 5 variables. And by simply multiplying out all the conditionals, for instance, you can calculate the probability of any given setting for any variable by multiplying the probabilities and say, okay, for that value, it is this probability. So this is just a way of specifying a joint probability efficiently by conditional probabilities. And CPDs of model depend on RNN. CPD means conditional probability. Those little tables we saw of probabilities are called CPDs, or conditional probability distributions of model depend on RNN design patterns. So we just saw the 3 patterns there, right? We are looking at only 2 of them here. The first one was recurrent connections between hidden units. And the second one is recurrent connections only from output at one time step to hidden unit. So these are the 2 models. So the CPDs depend on the, so if you, which is the model you're using, what kind of probability distribution. In feed-forward networks, our goal is to minimize this one, all right? This is the expectation comes in because we are doing the likelihood. This is the log likelihood is what we're using, and we are minimizing the negative log likelihood. That's where the negative comes in. Otherwise, it's a positive likelihood, log likelihood, which is the cross entropy between distribution of training set data and probability distribution defined by the model, because X, the expectation with respect to the data, sum over all the samples. And for definition, so we say it's a cross entropy between the distribution. So I'm kind of reminding you what why are you calling it cross entropy is because you know, it can be explained in this way. What is the definition of cross entropy and so on for discrete distribution? That's what it turns out to be. As with feed-forward network, we wish to interpret the output of an RNN as a probability distribution. With RNNs, the losses are cross entropies between the targets and the outputs. Mean squared error is the cross entropy of loss, okay. And with a predictive, we just saw a simple, you know, sequence lengths that are common. A predictive log likelihood training objective is this. And we train the RNN to estimate the conditional distribution of next sequence element given the past inputs. Alternatively, if the model includes connections from output at one time to next step, this is the second model. Conditioning predictions on past Y values. Decomposing a joint probability over sequence of Y values as a series of one-step probabilities predictions is one way to capture the full joint distribution across. And says, do not feed past Y values input for the next step prediction. And do feed the actual Y values, not the prediction, back into the network. And so there are a couple of different ways of dealing with the past outputs, Y values of the past outputs, using them or not using them. All right, okay, what is a simple example? RNN models a sequence of scalar random variables with no additional inputs. So this is the outputs. Input at time step t is simply the output at time step t minus 1. And yeah, that's the model we're using, the teacher forcing model we talked about. RNN defines a directed graphical model over Y variables. Okay, that's what it is, over the Y variables. We parameterize the joint distribution of observations using this. We talked about the language model that's output. So we're saying here is the output sequence. So give us a probability distribution over all the words in the language. Most likely value is probably going to be your caption, right? So that's the kind of thing that's being talked about here. So it's a probability distribution over all the outputs. So parameter is joint distribution of observations using the chain rule for conditional probabilities. Okay, any distribution can be written like this. This is the standard chain rule where you got all these dependencies. Negative log likelihood of a set of values, we convert that to a log, take the log of it and take a negative of it is going to be the loss function here. So a fully connected graphical model for a sequence. Supposing I say, well, here is a sequence of words, right? This is a market of vegetables, right? That's a sentence here. So those are the words in the sequence. And a fully connected model, every word depends on every previous word, right? So we got all these links here. And some are shown dotted and some are not shown solid. Okay, let's see. Maybe the last one is being forgotten. Maybe. Yeah. Anyway, so a fully connected model is being shown here. Fully connected graphical model for a sequence. Every past observation yi may influence the conditional distribution of some yt for t. So this would be the graphical model, a naive graphical model for a sequence of words that is dependent on the previous words. Every past observation influences the conditional distribution of some yt for t greater than 1. Parameterizing this way is inefficient. You're going to have to deal with every possible combination. Each of these outputs dealing with a very large vocabulary. So you would need a table. The CPD table we just saw would be enormous or humongous. And for example, take a look at this Y3. Its parents are Y2 and Y1. So we would have to parameterize the values here based on the previous values. A huge table. Let's say Y5 depends on what? It's got so many parents, right? It's got Y4, Y3, Y2, Y1. All of them are parents. So this is a hopeless parameterization problem, computing probability for every word given every other word. RNNs obtain the same full connectivity, but efficient parameterization as shown next. So this says if you want a probability distribution for all words in the English language and you have to calculate the probability for any given sentence, it is impossible to use an exhaustive method like this, but you use an efficient parameterization. And this is what an RNN really does. We saw these things. The Y1 at one time step is influencing the hidden node here. And then the hidden node is influencing Y2. This is the outputs, right? So the Y's are output, not the inputs. So the output is influencing the H. And the previous H is influencing this output as well as this, right? So you have introduced stages. So even though the deterministic function of inputs, so we get efficient parameterization over here. So then output is what causes the next hidden value here. Every stage in the sequence for HT and YT involves the same structure and can share the parameters with other stages. So this dependency is an interesting one. The outputs are influencing the state, and the state influences the next output. And that helps determine the next state. So this is the kind of model that they're looking at. It's a very specific model. It's one of those architectures.
Professor?
Yeah.
There is a question.
Yeah. What's the question?
The question is, do we use trigrams and bigrams while generating negative log likelihood at each yi?
Okay, well, you are asking a very specialized question here. See, we could always say here, like Y5 does not depend on all Y4, Y3, Y2, Y1, as it's shown here. And we can say, let's use, maybe the dotted ones are like that. It's using Y4. Okay, for this dotted lines are for the prediction. No, this model here is not limiting its scope. If you say bigram, it says a word depends only on the previous word, and you forget about all the previous ones as parents. A trigram would take the previous two, right, like that. N-gram would be some previous N. So those would all, so we are kind of trashing this whole model here, saying this model would be correct, where we aren't even introducing the approximation using bigrams or trigrams. We are saying, what if we depended on everything in the past? And that is extremely inefficient. That is why we end up with saying, okay, what if we looked at 3 of them in the past, or 2 of them in the past, or 1 in the past, bigram, trigram. Even then it is kind of, a rough approximation. So we are saying, let's move beyond simple dependencies. And RNN does these things in a clever way that it is somehow representing the state, you see, is a standard fixed length vector. So it is achieving some kind of memory by using these vectors here. So it's a different approach. It's a state variable. Okay, so this is not based on bigrams and trigrams where we are explicitly dealing with which word depends on which other word. This is forgetting all that. This is kind of saying all the words you have seen before is captured by this one vector. And that is the summary of all the past information. So anyway, efficient parameterization in RNNs is if y can take k different values, well, that could be the words. The tabular representation would have order k to the tau parameters, right? If we had a word that can take 10,000 values, vocabulary, then it would be order of 10,000 to the length of the sequence tau. By comparison, because of parameter sharing, the number of parameters in the order is order 1 as a function of sequence length. So a tabular representation where you have, that was the earlier one, the bigram, trigram we talked about. You would have the CPDs given that those are called tables or CPDs, conditional probability distribution tables.
Professor?
Tabular. Yeah.
There is another question.
Yeah.
Okay. At what time step or how frequently do we update the model parameters theta in RNN?
Yeah, in RNN, we kind of are fixing the view is over the last tau steps. Okay, so we're saying 10 steps or whatever, right? That's being fixed. And so we are, as we are moving along, we're just working with the previous 10 steps. So we saw that at time t, t-1, t-2, like that, right? So we are kind of fixing that as to how much we are looking back. So, so as we are observing new and new words, we are updating all these parameters. So that is what's going on here. Does that help? No? So it is just,
Yes. Yeah.
okay. All right. So let's see, even with efficient parameterization of PGM, I guess that's what the bigram, trigram, that would be efficient parameterization of probabilistic graphical model. Some operations are computationally challenging, difficult to predict missing values in the middle of the sequence. Price RNNs pay for reduced number of parameters is that optimizing parameters may be difficult. So RNN is a clever approach where we are using all the latent variables. Those of you who are taking the image retrieval course or the information retrieval course, 535, may be exposed to ideas like latent semantic indexing and all that, where again this idea comes in of summaries are being maintained somehow and you're not explicitly dealing with things. Okay, that's what's happening here. So latent variables have this power. Think of it, when you had images, we captured the features and forgot about all the details of the image. The features are what are needed to do your classification. Same kind of thing with language here. You got all these words, forget about the words. We have some kind of a representation we're getting. We don't explicitly work with, this word depends on this word, that would be your bigrams, trigrams and all that. No, this is not what we're doing here. We are kind of summarizing all of it with the latent units. Those are the features. So in a way, we can capture the same information as in the PGMs by RNNs. So PGM is probabilistic graphical model. There are two directed graphical models. Stationarity, that's a statistical concept. Parameter sharing in RNNs relies on assuming sample parameters can be used in different steps. So we said that all these parameters are being used again and again. W, V, W, W, V, W, W, V, W. They're not like every time step there is something else coming in. Same set of parameters. Equivalently, CPD over variables in time t+1 given the variables at time t stationary. So in a sense, there's a stationarity means when you have a time series, the probability distributions or dependencies doesn't keep on changing with respect to time. So in principle, it's possible to use T as an extra input at each time step. Learner discovers time dependence. How to draw samples from the model. So if it's capturing samples, simply sample from the conditional distribution at each time step. One additional complication, RNN must have some mechanism for determining the length of the sequence. All right, so that's some issue. Methods for predicting end of sequence, some specialized issues here. Let's skip that. Ah, that's it. Okay. All right. Let's see how we. Let's do one more. 10.2.3. There's just such a rich set of topics here. Rich in the sense they are really interesting. So there's really no time for in one course on deep learning to cover so many interesting issues here. So let's go on to the next topic, which is something we've seen, bidirectional. Okay, what are the topics remaining? Bidirectional and encoder decoder sequence and deep, so on. Okay, let's do this one. Okay. Bidirectional RNNs. I already covered it in the overview a bit. What is interesting about this set of slides from what I said about bidirectional RNNs earlier on is we actually look at the computational graphs, which is kind of important to know what is the computation involved in a bidirectional RNN. First of all, in need for bidirectionality. In speech recognition, the correct interpretation of the current sound may depend on the next few phonemes because of co-articulation and the next few words because of linguistic dependencies. While I'm speaking, if you're trying to get an automatic translation of that, I might have mumbled some word and it gets clarified only on the next word or next sound or next word or later and so on, right? So the interpretation of the earlier word depends on the future word. Also true of handwriting recognition. I'm trying to write something here. It looks like a chicken scratch. And later on, it becomes very clear what is the word here. Or the next word tells you what the previous word is. So it says backwards is also important, not just forwards. So a bidirectional RNN that's not just going left to right is to combine an RNN that moves forward through time from the start of the sequence, another RNN that moves backward through time beginning from the end of the sequence. So assuming you have the whole thing recorded, right? And so assuming that you can, maybe some sample that you have, that you first obtain the signal, and then you are able to do that. And for the next signal, you wait and so on. A bidirectional RNN consists of two RNNs which are stacked one on top of the other. The one that processes the input in its original order and the one that processes the reversed input sequence. The output is then computed based on the hidden state of both RNNs. So now comes the issue of how do you connect up the hidden states? And that is all explained over here. You have a time sequence xt minus 1, xt plus 1, and those produce the hidden units ht minus 1, ht, and ht plus 1. And this is producing a G. Okay, the G comes directly from X. So the HT, this is a time sequence in the forward direction. The H's are in the forward direction. G's are in the backward direction. The X's are influencing the G's. So you have a H sequence and a G sequence. And then this output is dependent on both the G sequence and the H sequence. Right? That's all. It's a very simple design where you have, so maps into sequences in both directions. H recurrence propagates to the right, G recurrence propagates. We call this the recurrence, H recurrence. Going this way and G recurrent. This allows output units OT to compute the representation that depends on both the past and the future. Apparently, this is a pretty important idea, like today's famous transformer models like BERT. The B stands for bidirectional, right? So it's a transformer model where the context is represented as a transformer, as a vector transform, right? Attention vector and so on. So parameters of bidirectional RNNs, bidirectional RNN is being shown here. Inputs, so it's more explicitly showing the units, xt minus 1, xt plus 1, ht minus 1, ht plus 1. This is the forward prop. And this is the backward prop. Oh, I'm sorry, I shouldn't call it forward prop, backward prop, because that's a totally different thing. That's for backward prop is for training. This is even the forward prop includes bidirectionality, right? So a deep bidirectional RNN, we got not only one layer but several layers, right? So this is showing 2 layers. I think this is a rightward arrow, leftward arrow, rightward arrow, leftward arrow. So this is multiple layers per time step. So I guess BERT must be using some version of that. Okay, that's it. There wasn't much to that one. Mohammed, how are we doing? Should we stop now or should I do one more?
Professor, you can do one more.
I can do one more. Okay. Yeah. All right. That's good because we are not meeting. By the way, those of you who joined late, we are not meeting next week due to the Thanksgiving break. And we meet again in 2 weeks. And I'll do NLP after we come back. This is all preliminary to NLP, but we have learned a lot of concepts that are necessary for NLP. So bidirectional we're done with. All right, so is that 10.2.4 that we need? Okay, yeah, I think this is an important topic. Modeling sequences conditioned on context with RNNs. And modeling sequences conditioned on context. We are still in recurrent neural networks, and there are all these other topics. We are just stuck on recurrent neural networks. We're doing 10.2.4, which is the last of these topics on recurrent neural networks. So graphical models of RNNs without and with inputs, directed graphical models of RNNs without inputs, fully connected graphical model. It's this one, the outputs probability distribution. And this one also didn't have any inputs. It was just modeling the outputs here. This is the RNN model. This is a state diagram. Or actually, this is a probabilistic graphical, directed graphical model. This is a directed graphical model. This is an RNN. RNNs do include a sequence of inputs, x1 through xt, and we show it explicitly like this. RNNs allow the extension of the graphical model view to represent to represent the not only the joint distribution over y variables, but also a conditional distribution over y given x. Okay, CPDs of model depend on RNN design pattern. We saw this. This is a previously repeated slide. Model 1, where horizontal connections. Model 2, where we have these diagonal connections. Extending RNNs to represent the conditional py given x. So a model representing a variable py theta can be reinterpreted as a model representing a conditional distribution p given y given omega with omega equal to theta.
Professor?
Yeah. Yeah, go ahead.
So this is regarding the Thanksgiving day. So the question is that the Thanksgiving break is from 25th, yet deep learning class is on Tuesday. So we will not be there on Tuesday.
Right, the Thanksgiving holiday is on Thursday. And so Tuesday being Thanksgiving week, we will not have a class, right? Wednesday also there are no classes. And okay, was that the clarification about Tuesday? Yeah. Oh, what about the Thursday meeting, huh? Yeah, I've been meeting with all of you on Thursdays for your projects. So we won't have that next week, right? But this Thursday, day after tomorrow, we'll have a project discussion. Actually, I could have one more on Sunday if necessary, all right? So if, let's see how it goes. Let's see how this Thursday goes, try and come to this. If you can't come this Thursday, we'll try and arrange. Yeah, it's a long break of 2 weeks. I can meet with you on another day rather than Thanksgiving Day is a Thursday. So we won't have the project meetings on Thursday, but maybe on that Sunday we can have it. All right, I'll let you know. Okay. I enjoy talking to you about all your project descriptions. So do present to me what you're doing, and if you've already presented to me, come back and tell me how much you achieved or how much you have not achieved and you're stuck. This is the time to discuss these things. So the end goal is for you to have done something and not simply a grade, that you have actually built something and you can be happy about it. All right. Back to extending RNNs. All right. A model representing a variable can be reinterpreted as one with conditional. This is a classic topic that occurs again and again when you have what are called as Markov models, and then we talk about conditional Markov models, or they're called conditional random fields. How do you condition them? We can extend such a model to represent distribution Py given X by using the same PyW as before, but making W a function of X. All right. In the case of RNN, this can be achieved in several ways. Most common choices are described next. Taking a single vector X as an extra input. Instead of taking a sequence as an input, we can take a single vector X as input. When X is a fixed size vector, we can simply make it an extra input to the RNN that generates the Y sequence. Common ways of providing an extra input to RNN are an extra input at each time step as the initial state H0 or both. The first in common approach is illustrated next. Okay, so this is showing mapping vector into a distribution. See, we are using an RNN to represent a probability distribution, which is kind of a very interesting concept. Because representing probability distributions is an extremely important concept, and a whole course is based on this, 674. But when probabilistic graphical models were being discussed, the idea of using RNNs there had never occurred. So this is a new phenomenon with deep learning, that you can use a deep learning approach to represent probability distributions. And we are just saying this X, an extra input at each time step. And there is another matrix R coming into play that is being shared all over here. And so interaction between input X and hidden unit vector H is parameterized by a newly introduced weight matrix R that was absent from the model with only Y values, appropriate for tasks such as image captioning, where a single image X is input, which produces a sequence of words described in the image. Isn't that clever? We just talked about language inputs and sequence of sentences and so on. And then we're saying there is an image of the market with the vegetables, and that is influencing this sequence. Each element of the observed output serves both input and during the training as a target. So that is the idea. RNN to receive a sequence of vectors as input. RNN described by, this is the usual activation function, corresponds to a conditional distribution. Make conditional independence assumptions such as this, so that this factorizes as Y is only dependent on X1 through XT. And so this is the product of all. That's why this product comes in saying all the Y, let's all the Y's be independent, in which case you can write it like this. To remove the conditional independence assumption, we can add connections from the output. Both sequences must be of same length. Removing conditional independence assumption, all right? See, this is all beautifully being done here in computational graphs, and it is showing how this can be done. Ah, that's it. All right, so there is a whole rich material here on tying up images and text and an important topic, and all expressed in great detail in terms of the computational graphs that are involved. That was very quick. Maybe I'll look at one more. 10.4. Encoder decoder sequence to sequence architectures. Okay, we have gotten out of recurrence neural network. That had like 4 parts there. Bidirectional RNN we looked at, and then encoder decoder sequence to sequence architectures. We've previously seen RNNs, an RNN to map an input sequence to a fixed size vector, RNN to map a fixed size vector to a sequence, right? Fixed size vector X to a sequence. How an RNN can map an input sequence to an output sequence of the same length. We saw this one, which is the horizontal lines, this one with the diagonal lines, and this one with, I guess it's about the same thing. We're taking the Y outputs here. And then we saw this bidirectional, right? Previously seen RNN. They're all different designs for recurrent neural networks. RNN, when input output are not the same length, right? Which is something we talk about in machine translation. What is this? In English, it might take 3 words, but in German, it might take 4 words or whatever, right? Here we consider how an RNN can be trained to map an input sequence to an output sequence, which is not necessarily the same length. Comes up in applications such as speech recognition, machine translation, or question answering, where the input and output sequences in the training set are generally not the same length, although their lengths might be related. So this talks about an encoder, decoder, or sequence to sequence RNN learns to generate an output sequence Y1 through YNY, given the input sequence X1 through XNX. So the length of this is NX and the length of this is NY. And what is the RNN architecture for this? So the encoder is taking X1 through XNX. And that is feeding into this C, it's the context. And that C is feeding to the decoder, it's Y1 through YNY. So it was not directly mapping X to Y, X to Y, X to Y. It is all summarizing into C here. It consists of an encoder RNN that reads an input sequence and a decoder RNN that generates the output sequence or computes the probability of a given output sequence. The final hidden state of the encoder RNN, the final hidden state of the encoder RNN is used to compute a fixed size context C, which represents a semantic summary of the input sequence and is given as input to the decoder. All right, so this is the key element. When we discuss attention models, we begin like this. Oh, the whole thing is encoded in one context vector. Maybe that's too small. Maybe we need more. So attention vectors do that. All right. So that is encoder, decoder, sequence to sequence RNN. All right. How about maybe one more? They're all very short little things. Okay, this is under recurrent neural networks or under sequential models. It's a deep recurrent networks. So parameter blocks. The computation in most recurrent neural networks can be decomposed into 3 blocks of parameters: from the input to the hidden state, from the previous hidden state to the next hidden state, from hidden state to the output. Okay, that's the obvious thing in any deep learning. Blocks of parameters as a shallow transformation. So would it be advantageous to introduce a depth into each of these operations? So that is an interesting question. Should you introduce depth here? Experimental evidence strongly suggests so, that we need enough depth in order to perform required transformation. Right. So I have heard both sides of it, that apparently for language translation, you don't need much depth. And you don't need like several levels of hidden units. Whereas maybe for image to captions, maybe you need that. So experimental evidence suggests that depth is good. Ways of making it deep. Hidden recurrent state can be broken or groups organized hierarchically. All right, H. There is a recurrence here, and this is we are writing the circuit diagram here, right? There's a recurrence here, and then one more level recurrence here before we get the Y. Or deeper computation can be introduced in the input hidden and the hidden output parts. So this is H is just the same one, but there's one more level on each side. And then the path lengthening effect can be mitigated by introducing skip connections. This one is, yeah, it's going to another node here and coming back. This is coming back directly here, so on. One of the dangers here is when you introduce more and more depth levels, the training becomes that much harder, right? The backprop BPTT is going to be encountering many more paths, and then all these practical issues like exploding gradients or vanishing gradient problem. So this takes up each of them, recurrent states broken down into groups, deeper computation in hidden, and introducing skip connections. The skip connection, hidden to hidden path, is something I think some of these methods like ResNet and so on, the practical methods that many of you would have used already, I think use some of these ideas. Okay, that's it. All right, Mohammed, are you ready to take over now?
Yes, Professor.
Okay, fine. All right, then I will see some of you on Thursday and maybe others on a subsequent Sunday. Send me some requests if you would like to meet with you on a Sunday. That way I know that there is some interest for me to schedule it for a Sunday, okay? There are a couple of Sundays coming up, so there could be 2 Sundays we could use.
Okay. All right. So